We're going to turn our attention now to studying the motion of springs. And at the start here, we're going to look at simple harmonic motion. So I'll explain what all that means as we move along. Now suppose we have a spring with nothing attached to it. Okay, and so this spring has a length of L0. Now we're going to attach a weight to that spring, and the spring will be stretched a bit. Here's our weight, and it's stretched a distance of L. And there's the original L0. So you might say with the spring, the natural length of the spring is L0. With the weight attached, you let it come to rest in equilibrium where it's not jostling around, it's just stationary. Then it stretches an additional length of L. Now, if we want to set this into motion, then suppose we stretch it down even further. So here's our spring down here, our weight. So we have this distance, L0. We have this distance, L. And this distance I'm going to call Y. So in other words, when the spring is in equilibrium, not moving at all, then this is where Y equals to 0. So I'm choosing as a reference frame system the y-axis such that the downward direction is positive. So as we go down, the y's become positive. So if I pull the weight down, then the displacement is y, the displacement is positive. And then what happens when we let go? Well, it's out of equilibrium. So when it's pulled out of equilibrium, then it starts into motion. And naturally it swings back up and starts bouncing. All right, well, how can we turn this into differential equations? Well, we need Hooke's law. And Hooke's law says that the amount of force exerted on a spring is counteracted proportionally by restoring force. Actually, it's not proportional, it's the same. So the weight, if I pull down, if the weight pulls down, then the amount of weight pulling down is held in equilibrium by the restoring force wanting to pull it back up. And so, for example, if I have 10 pounds being pulled down, the spring is exerting 10 pounds backwards, then there's a standoff. The weight is not moving, is it? So we can start to put some quantities on this. Weight is mass times gravitational acceleration, mass times acceleration attributed to gravity, and it's proportional to the length of the spring. That's where Hooke's law comes into play. That restoring force is proportional to length. So it's going to be some constant number, K, times L. Now K will depend upon the spring. How strong is the spring? And so that very weak spring will stretch a long way, and a very stout, heavy-duty spring will only stretch a little bit. And so the K depends upon the makeup of the spring. And so, all right, so the weight going down is balanced by the restoring force, which is proportional to the length that's been stretched. That is Hooke's law. And so we have a kind of an important thing here. Now, it turns out, well, I'll say that for a moment here. We'll work with this a little bit. All right, well, let's put this into motion and see what happens to it. I've written a sensible equation up here. The net force on a spring system is what? It's the amount of force coming down minus the amount of force going up. Now when these are equal, when the force coming down is weight, and it's balanced out by the spring entirely at the equilibrium position, which is L, then these two are equal, the net force is 0. Not too interesting. You know, the spring is not moving. But if we pull it out of equilibrium, then that changes things. And so the net force, and by the way, here, this distance, when it's been stretched, pulled down out of equilibrium, the total distance is L plus y. So I need to erase this picture to make room for the differential equations. So keep that in your mind there. Here's my differential equation approach. Y of t is going to represent position at time t. And what happens when you take the derivative of position? You get the velocity at time t. And the second derivative is the acceleration at time t. So the net force is weight. Well, force is mass times acceleration. Newton's law, force is mass times acceleration. So the net force on our system is the mass times the acceleration, y double prime. Now the force downward, if nothing else is working on the system, then the only force downward is the weight. The weight is mass times gravitational acceleration. What about the force up? Well, we determined that the force was proportional to length, and the constant proportionality is k. But when it's pulled out of equilibrium, pulled down in that last picture, then the length has been stretched from equilibrium to be L plus y. So here's our kind of a basic differential equation describing this system, and it's a very simple description. It really is not realistic. And I'll explain that to you in a moment. But let's do some erasing here. Now I'm going to distribute here and collect up terms. So I have m y double prime equals to mg minus kl minus ky. And you notice, well, we've seen these before. There's weight, mass times gravity. We've seen kl, mg equals to kl. And so these literally cancel one another. And if I bring this y term to the left side, I've got m y double prime plus ky equals to 0. And another finesse is to divide by mass. So divide by m, y double prime plus k over m times y equals to 0. Great. All right. Now, an alternative to k over m, if we look at this mg equals to kl equation down there, relationship, if I divide both sides by m, is that right? And both sides by g, nope, both sides by l, then I've got g over l. Is that what I want? G over l is equal to k over m. That's what I wanted. So I have another way of writing this. This would be y double prime plus g over l times y equals to 0. All right. Well, I kind of like this form myself right here, the g over l form. But it depends on what how are you measuring things. You know, if you know the length, the natural length of the weight on the spring, then you'd have length, and g is gravitational acceleration. So if you're working in the English system, it's 32 feet per second squared. If you're working in the metric system, it's 9.8 meters per second squared. So I'll try to work problems in both systems, so you have those, because this book has problems in both systems. Now nowadays in physics you normally only work in the metric system, so but I'll do some of both. All right, well, let's I'm going to do some erasing, and then we'll solve this problem right here. I copied our equation up here, y double prime plus g over L times y equals to 0. And it says g and L are constants. It's a second order linear differential equation, homogeneous with constant coefficients. So the characteristic equation would be m squared plus g over L equals to 0. Now this m is different than mass. It's the characteristic equation m. So m would equal to plus or minus the square root of g over L times I. We get an imaginary number because when you plot this over on the right side, it becomes a negative g over L. And then take the square roots and you get the square root of a negative, which is an imaginary number. Both g and L are positive quantities because gravitational acceleration is downward. That was positive direction. And the stretch length was measured downward. That's positive. So bring this over, it becomes a negative, which generates this imaginary number. Now, there were 4 ways to write this. One involved literally e to this power. But another way of writing this is y of t would be c1 cosine square root of g over L t plus c2 sine square root of g over L t. So that was an alternate way of writing this solution. We've covered this before. And it turns out that's not too practical. The other 2 ways of writing it are the most practical, where we combine these into a single sine or a single cosine. And so as a cosine, it's c cosine square root g over L times t plus delta, a phase angle delta, or it's y of t is c sine square root g over L t plus delta. So we could write it as a sine or a cosine. Now these deltas would, I think, would definitely have to be different. And but this is, if you're using this book, those are listed on page 325. 325. And now the author is using k over m. I'm using g over L. So, but they're interchangeable. All right. Well, what do these will look like? So let me erase the middle here. So we set up a spring problem with a rather simple assumption that when you hang a weight on it, it stretches down, and then we let go. Now, what's so simple about that? Well, we left off friction, the frictional characteristic of a spring. You know, spring bounces up and down. If it's in a medium like air or water, then it encounters resistance. And even if it's in a vacuum, there's still resistance within the metal of the spring, for example. And so there has to be resistance, otherwise there would be perpetual motion. And we know that's not true. Perpetual motion doesn't exist in a machine type situation. So this is ignoring that frictional characteristic. And we'll put that in. These problems will get more interesting when we put the frictional characteristic in, but that all in due course. Without that assumption, here's our problem, here's our solution. It's one or the other of these. And what do those look like? Well, sine and cosine are wave patterns. And so, literally, as time progresses, here's time, t, and I didn't do that very well. I meant to put my axis right through the middle of that wave. So let me fix that. Alright, so yeah, we have a wave pattern generated here. And there we go. Right through the middle is what I meant. a sine wave or a cosine wave, they're both the same except that they're at different phase angles or different displacements on the axis. You know, cosine starts at a different position vertically than sine does. But in any event, they look like this kind of wave pattern, and it bounces up and down. So, for example, if we pull a spring down 3 inches, and there's no frictional characteristic, it's going to bounce up and down 3 inches either way of equilibrium, which means the amplitude is 3 inches. 3 inches both ways. Left to right is described by time. As time flows, the displacement or position y changes up and down, up and down, up and down, up and down. So you can kind of imagine a bouncing spring plotted out on time would result in this kind of sine wave or cosine wave graph. That's the idea. Okay, well, I think I may have mentioned that the choice of sine or cosine really depends upon the problem and your convenience. So we'll get into discussing that. All right, next I'm going to do a real simple example of this simple harmonic motion.